Welcome back. Happy New Year and welcome to my virtual classroom. It's great to be back working with you guys once again. I thought I would make a few videos of the lessons to go along with our in-person learning just because you may want to start and stop a lesson to take notes or whatever you need to do, and this just gives you flexibility. This unit, we're going to look at light and optics, and while it would have been nice to do experiments in the classroom, I have included a number of gizmo labs that I will have you do. In order to do that, we're going to have to get you um, signed up with gizmos, and we'll work on that another time. But for now, let me introduce this unit that we call optics. Well, the first thing we have to do is figure out what exactly is light anyways. Well, obviously light is a form of energy. You've seen some of the chemistry examples I've done where light's released, and certainly that is energy. So it is a form of energy. Light also travels in waves, just like sound, just like water. So if you've been to the beach and you've swam on a really wavy day, you know firsthand that those waves can be really big or quite small. And we'll talk about the size of a wave in a minute here. You can compare waves to a bug floating on water, and maybe you've seen this kind of picture before, where initially the bug is kind of sitting on the water before it hits a wave, and then when the wave comes to the bug goes up, and once the wave goes by, the bug goes back down again. So that's basically the idea, and light does behave the same way as water and sound. Let's talk about wavelength again. For those of you that have swam on Lake Erie, I think you'd agree it's a very dangerous lake. And the reason why it is because the waves are so close together, and they're not real big waves, but they're tightly condensed and they can overcome you pretty quickly. So let's take a look at the parts of a wave, which again, water works great when you think about it. The highest point in a wave is obviously the crest. So there's one there, there's one there. That would be the top of the wave. The bottom part of a wave is the trough. And that's the same sort of lingo that we would use with water, of course. A wavelength is a distance from one crest to another. So in this picture, we're looking at this distance right here. And of course, the closer those crests are together, the tighter the wave, the more energy it has, the more dangerous it is. The amplitude of a wave is simply the height. And so in this case, we have quite a high wave when you go from the bottom of the trough up to the top. That's pretty high. That's a tight wave and has quite a high amplitude. The term amplitude also comes into sound waves. If you're interested in sound systems, amplitude matters in terms of the sound quality. All right, let's see if you can figure it out. Can you order these waves from shortest to longest? Well, I'm hoping that you will say this bottom wave, which is high frequency, has a short wavelength, so it would be the shortest. The medium frequency wave would be the middle one, and the low frequency wave would be the high one. And we'll talk about this in a minute. The more dangerous waves are high frequency, where they're close together, shorter wavelength. The top wave is less dangerous because its wavelength is longer and it has a lower frequency. We're not going to get into this too much in this course, but there is a mathematical relationship among the speed of a wave, the frequency of the wave, and the wavelength of the wave. If you think about a tsunami, Again, I'm referring to water, but a tsunami is a great example of a wave that goes really fast. And that makes it dangerous because it has more energy. And so we'll talk about that here in a second. This is our triangle that we use. Basically, you can see wavelength is down here, and it doesn't matter in this course, but the Greek letter for wavelength is lambda, and frequency is F. If you listen to the radio station, maybe you listen to Star 104, 103.7. I tend to listen to Q107. I like their morning show and their after hour show. And of course, the speed of the wave is meters per second. So the speed is equal to the frequency times the wavelength. The wavelength is equal to the speed over the frequency. Bottom line is, as the wavelength goes up, the speed goes down. And as the wavelength goes down, the speed goes up. So that, my friends, is a very quick introduction into waves. And we will continue on our journey by looking at the electromagnetic spectrum next, which is what we can see. And that will relate well to the wave theories of light and colors. And we'll even look at the human eye at some point.